Okay, so I hope you see the screen. Yeah, okay. All right, so I stopped in the middle. And I was introducing a few aspects of string theory and just those aspects that we need to understand where gauge gravity duality comes from. Okay, so and the last thing I told you before the break is that in string theory, there's open strings. So these are strings that have endpoints, and then there's closed strings. So that's strings that don't have endpoints. And they have different types of vibration modes. Okay, and the vibration modes of this open string gives you a gauge field, and the vibration modes of this closed string gives you a graviton. So, and in fact, now this is already also an ingredient of the duality, that we can look at string theory in this, looking at open strings and looking at closed strings. And looking at particular objects in string theory, the so-called D-branes. In the open string picture, we get our gauge theory, and in the closed string sector, we get the gravity theory. Okay, so that's what I want to explain. Okay. All right, so maybe you have heard also about string theory, that if you quantize string theory to get a quantum theory of gravity, string theory has the feature that if you look at supersymmetric string theory, that it's well defined in 9+1 dimensions. So that's some consistency of the quantum theory. So you don't want tachyons, you don't want anomalies, so which are kind of unwanted effects in physical theories. And that means you have to look at your theory in 9+1 dimensions. Okay, so obviously our world is not in 9+1 dimension, it's in 3+1 dimensions. So then you have to explain what these additional dimensions mean. Now there's one area of string theory where people essentially compactify these dimensions. So they rub them to make a very small circle. And then they study the physics of these compactified dimensions. But that's not what we do here in ADS-CFT or gauge gravity duality. So we take another route, and the other route is to look at the so-called D-branes. Okay, so now I want to explain to you what a D-brane is, because that's the key to understanding what the ADS-CFT correspondence is. So what's a D-brane? So the D-brane is a hypersurface embedded into this 9+1 dimensional space. Okay, so it's very hard to imagine. So imagine you have a space which has 1 time and 9 space directions. Okay, I know this is super abstract, but the consistency of the theory requires that we have this. Okay, but then we say now our real world is in 3+1 dimensions, and we can achieve 3+1 dimensions by looking at a subspace of this 10-dimensional space, which is 3+1 dimensional. And this space would be spanned by a so-called D3 branes. Okay, so why D? So D stands for Dirichlet boundary condition. Okay, and 3 is the number of space dimensions. Okay, so we have 3 space and 1 time direction. And so now, so if we have this hypersurface, we can think of our real world being embedded into this higher dimensional space. Now, these Dirichlet boundary conditions are boundary conditions for the open strings. So we can think of some open string as drawn here with this red line. And so this open string needs some boundary condition, like the string in your violin needs to be attached to the endpoints. And so the open strings, they may end on these hypersurfaces, and then they can vibrate. And these vibrations, they give the dynamics in our theory. And that will lead actually to a gauge field. Now, if we take this low energy limit that I've been mentioning before, this means we get a gauge theory on this 3+1 dimensional surface. Okay, so you see it's a very mathematical construction. But you will see why I'm talking about all this, because this provides a key to the duality that we want to understand. Okay. And so at the very beginning this afternoon, I mentioned the low energy limit, which means we go very far away from this brane, okay? And then if you go very far away, it means these strings become very small and you can't see anymore that they extended, they look like a point. And then in the low energy limit, the strings become point-like again. And in that limit, these vibration of these open strings, they just give us our gauge theory. So the Lagrangian involving the gauge theory describes the fluctuation of the branes in the limit where we only look at the low energy fluctuations. So essentially it's the fluctuation where the string, like the string in a violin, is attached at the two ends and just goes up and down like this, okay? So that corresponds to a gauge field. And this we get from this low energy limit of these open strings. So the open strings and the low energy limits give us the dynamics of the gauge fields on the brane. Okay, good. So that's for the open strings, but now we also need to talk about the closed strings. And so in fact, that's also at the origin of this duality here, that these D branes, although they're the same physics, can be understood in two different pictures, okay? So in the open string and the closed string picture. And so far I explained to you the open string picture, but now I have to explain the closed string picture. So the second interpretation of the D branes is that they are solitonic solutions of 10-dimensional supergravity. Okay, so what does this mean? Okay, so I told you that the string theory is defined in 9+1 dimensions. And so now I can solve the equations. So in physics, we always solve equations of motion, okay, which we get from the Lagrangian. So there are these Euler-Lagrange equations. And I can look for solutions to the equation of motion for wave packets that don't disperse. Okay, so that's what a soliton is. And so I can find solutions to my 10-dimensional gravity equations of motions that preserve the 3+1 dimensional surface. Okay, so it's a particular solution of the equations of motion, which preserves the 3+1 dimensional subspace. And so the key feature of these solitonic solutions is now that they are very heavy. Okay, so they have a mass. And because they're so heavy, they curve the space around them. So then you can think, you solve these gravity equations of motion, and then you have a subspace, which is like a sheet or a tablecloth or something like this. So a tablecloth or a sheet is a 2-dimensional object that is embedded in 3-dimensional space. So in the same way here, we have 3-dimensional objects embedded in 9-dimensional space. Okay. So imagine this sheet. So imagine you and a friend hold each end of this sheet or tablecloth. And then a third friend comes with a big pumpkin, okay, and puts the pumpkin on the sheet. And this will then curve your space, okay? Because so it's very heavy, so it will, so if you know Einstein's theory of general relativity, so curvature and mass are actually the same, okay, and the same also happens here. Okay, this is maybe very complicated. So are there any questions about this? Okay, are you familiar with this concept, or do you want me to explain more?
May I say something? At a certain point, you said that to to avoid anomalies and tachyons, we must coach string theory in 10+1 dimension.
Yeah.
But in general, in the history of physics, when we have something that from the mathematical point of view is strange, not always we make this kind of elimination. Think, for instance, to the case of Maxwell equations that prelude the possibility of waves or retarded waves. These waves that come from far and arrive in the source. This is clearly physically impossible, but it is not, even if it is a possible solution of Maxwell equation, we not eliminate the Maxwell equation only for this reason. So I would like to understand if it is the reason to choose this dimension is why it's so strong, because in general mathematics it is easy that it's much more richer than reality. So why do we consider it so important to avoid this kind of situation?
Yeah, well, okay. Well, I don't think we want to avoid the situation. We just want to somehow interpret this. So okay, what I'm trying to do is to interpret how this is actually viewed. Okay, so well, I mean, okay, I think it's fair enough to say that obviously our world is in 3+1 dimensions. Okay, so we have X, Y, Z in time. Okay, so I think it makes sense to say, okay, we want a theory that is in 3+1 dimensions. But then obviously there's this question, okay, but in this string theory, we have more, we have 6 dimensions more. Okay, so they must have some physical meaning if our theory makes any sense. And so here there are 2 possibilities how to make some meaning out of the 6 extra directions. But in fact, both of them have in common that somehow these extra dimensions, they are identified as particles, okay? You kind of view these extra dimensions as being fields in your quantum field theory. So let me try to explain. So assume that this is the 3+1 dimensional surfaces which are real world, okay? Then obviously you have fields that, so there's an extra, there are many extra dimensions, there are 6 extra directions in this direction. But what you can do is you can write a Lagrangian for this theory here again, in which these extra dimensions show up as fields in this theory. Okay, does that make any sense? Probably I should. Did that partially answer your question? Or?
Answer to a question, but not to the one that I posed, but to another that I have in my mind.
Okay. So, okay, let me try to answer. So can you repeat your original question?
I was not able to explain my point. Yes, your answer is very interesting for me because it is an answer to another question. That is, what are the 6 dimension more? No, my question is a bit different. I'm reading your books. I saw that at a certain point you said, as you said also 10 minutes ago, that we have to build string theory in 11 dimensions because else there are tachyons. Okay, so my question is this kind of reasoning, that is, we want to avoid tachyons. Are we sure that is completely necessary? Because in other situations in physics, mathematics is much more richer than reality, but we do not throw mathematics only because we have more possibilities than what we find actually in the observation. So my question is it possible to make a string theory only with 4 dimension, or as we expect with tachyons that is able to explain something for some reason is better than level, or it is a completely impossible Rosno research? Perhaps I don't know if I am able to explain the point.
Yeah, okay, so okay, yeah, I try to answer. So originally, of course, string theory was invented in the 60s as a theory of hadrons, and so which was then replaced by QCD. And that was a string theory in 4 dimensions, of course. Okay, and this string theory in 4 dimensions, since it was not in 10 dimensions, obviously it had tachyons and anomalies. But there people really compared to measurements. I mean, in the lab, I mean, they were looking at these rigid trajectories, okay? But then, I mean, these tachyons just don't exist in nature, okay? So if you have a theory with tachyons, that's fine, but then if you in the end want to describe some physics in the real world, it turned out that, you know, these particles just don't exist. So then obviously your theory doesn't make a lot of sense. I mean, from a very basic point of view. The other thing is that, I mean, if you have tachyons and anomalies, I mean, the theories are built in such a way that they also mathematically, you know, lead to contradictions if you have these structures. And I mean, so that's another reason for not wanting them to be around. I mean, the anomalies maybe is easier to understand. So string theory is meant to be a theory of quantum gravity. So this means you want, so you can think of general relativity as a theory of coordinate transformations where, you know, all coordinate systems are equal and so on. But if you have an anomaly, this is no longer true. Okay, so if you want a theory of quantum gravity and your diffeomorphism invariance, so your coordinate transformation invariance has an anomaly, which means the symmetry is broken, then it doesn't do what you wanted it to do. You want a theory of gravity where all the coordinate systems are equivalent, and if there's an anomaly, this is no longer the case. And then you know, just conceptually, the theory is not very well defined. I mean, so okay, the short answer is, I mean, there's both consistency reasons just at the mathematical level, as well as the fact that if you do string theory in 4 dimensions, the theory predicts particles which don't exist in nature or have not been seen in the lab. So, and both of them are reasons for discarding such theories. So this is called non-critical string theory. I mean, sometimes people still consider this, but then, you know, there's always this issue. I mean, what do you want to describe with your theory? And certainly as a theory of strongly interacting particles, that theory, I mean, QCD is much more successful. Okay.
That doesn't work.
Yeah, it just doesn't work. I mean, okay, it predicts particles that have not been seen. Okay, so and they must have, you know, it predicts particles at particular energies where they're not seen, and then, okay, then obviously the theory doesn't describe nature. Okay, so I mean, so there's both reasons that it predicts particles that are not seen, but there's also consistency reasons that make your theory mathematically inconsistent. Well, it's just not a theory of quantum gravity anymore, but that's what you wanted to have. Okay, so then, so you know, there's if you set out to make a theory of quantum gravity, and you say it should be based on string theory, then only if you work in 9+1 dimensions is the theory that you get a meaningful theory of quantum gravity. And of course, that's what you want to have. And if, you know, otherwise it's not then it's something else. But I hope maybe did this answer your question? And
yes.
Okay.
Next time you write a book on duality for philosophers, spend much time explaining this point.
Okay, very good. Well, okay, yeah, I agree. This is, you know, sometimes physicists, they think they take things for granted, or, you know, they say we absolutely want this or that for some reason, and maybe you think it's not really necessary. But here, I mean, it's really, I mean, you know, if you have anomalies, then the theory is just not a theory of quantum gravity, but that's what you wanted to have. So then you know, the theory is just not a theory of quantum gravity. So then, but on the other hand, it's also not a good theory of hadrons because it predicts particles that are not observed. So yeah, I mean, so yeah, I'm not sure if this is very methodical, but, you know, just these are really unwanted features that we don't want to have in our theory. Okay. Yeah, I know sometimes maybe if I go too quickly and I say, oh, let's have this or have that for some reason, maybe we should be more careful of understanding exactly why we want particular features. Okay, so the reasoning is, we want a well-defined theory of quantum gravity. And if we use string theory, we only get a well-defined theory of quantum gravity if we work in 9+1 dimensions, because of these tachyons and anomalies. So, and these are features also unwanted from a mathematical perspective if we just consider, if our only criterion is to have a mathematically consistent theory. So then obviously we have 6 dimensions too many. And then, so what do we do with them? And then there's 2 options. Either we look at this complication or we look at D-branes. Now, today I want to tell you about gauge gravity duality, and this is based on using the D-branes. So that's why I only focus on D-branes, but not on the compactification. Okay. Okay, so, and then I explained to you that we can have either open strings or closed strings. And these D-branes, they can be interpreted either in the context of open strings or in the context of closed strings. But they're, of course, the same object. You know, they're these surfaces, this black thing, this sheet here, okay. And, okay, so now I have 2 interpretations of these branes. And now, so let's go really all the way back to this thing which I showed very early in my talk, which is, sorry, this picture, okay. So the physical system now are these D-branes. And I have one theory with open strings and one theory with closed strings. In one case, you know, this is the surface where the open strings can end. In that theory, it's the solitonic solution to my supergravity equations of motion. And then I say, okay, because these 2 theories describe the same physics with a different Lagrangian, different degrees of freedom, they must be related by a duality. Okay, so I'm precisely using this picture now. So that's the reason why we do this. And we have these D-branes, and on one hand side, they're interpreted in the open string picture where they give rise to the dynamics of the gauge field in the brane. And in the closed string picture, that they are the solitonic solution of 10-dimensional supergravity, which are heavy objects that curve the space around them. Okay, so now this leads us to this picture. And so this is a short picture of the ADS-CFT correspondence, okay? So now the idea is to have a gauge theory, you don't just have one brane, but you put many of them on top of each other. That's why there's, so that's depicted here with these 3 lines. Okay, so I have now 3 of these sheets on top of each other for an SU3, but now we want n. So we have n branes on top of each other. And so these branes are my physical system. And here's the open string and the closed string picture. Now, in the open string picture, I have open strings attached to them, and there's these Dirichlet boundary conditions of the surface. And these can fluctuate, and this gives rise to these gauge degrees of freedom. On the other hand, this is in the closed string picture, this is a very heavy object that curves the brane, the space around it. And now if you do the mathematics, if you solve the equation of motion and take this near low energy limit, you get precisely, so our space was in 9+1 dimensions, okay? And so this decomposes into a product of a 5-dimensional anti-de Sitter space and a 5-dimensional sphere. AD is 5 times S5, okay? And the excitations in this space are now the closed strings. Okay, so that's at the level of the branes. But now, so this is the question that somebody asked at the very beginning when I was talking for 5 minutes, but I think now this probably should be the answer to the question. Now, if I take a particular low energy limit, so this is the great invention by Maldacena, and this is this low energy limit. So if you take a low energy limit, this open string picture gives you precisely this SUN NX4 supersymmetric gauge theory in 4 dimensions. So the fact that n goes to infinity means that I have n of these branes on top of each other, and then I take an infinite amount actually, but they're all coincident here in space. But if I take the same low energy limit in this other picture, then I get a gravity theory on this particular space, AD is 5 times S5. Okay. And so now I can close this diagram and I can say, well, if these two things are dual to each other in the sense that I explained at the beginning, in this very schematic way of defining duality, then these things also have to be related. Okay, so that's the logic. Okay, so probably this was too fast. So, I mean, you know, this is really one of the key points, so I should go slowly and explain one more time probably. So the duality is between the physical objects are these three branes. And now I have two theoretical models in which they appear. They appear in this open string and the closed string picture. In the open string picture, they give rise to this gauge theory in a particular low energy limit. But the same low energy limit means that this curved space around them precisely contains this ADS5 space. Okay, and so the duality is really because these objects are the same, described in two different scenarios by two different theoretical frameworks and Lagrangians. Then after taking the same limit, it means that also these two theories must be dual to each other in this sense. Okay, and so then this means here I have a theory without gravity, and here I have a theory with gravity. And so, of course, the symmetries play a big role again, because the global symmetries of this theory, which I haven't written down here, correspond to the global symmetries of this particular space. Okay, now please ask me questions about this figure, because this is really, I mean, so why am I showing this figure? Because, you know, if I just tell you like this, well, here I have a quantum field theory and here I have a gravity theory, and actually I tell you they are the same, then you should say, why should I believe this? Okay, there's absolutely no reason why they should be the same. But then I can answer and I say, well, there is a reason why they should be the same, and the reason is what is shown on this slide. Okay.
Excuse me.
Yeah.
I think I'm missing something. What's the role of the embedding space in this in the D3 brane side of the duality? Because
yeah.
Yeah, okay, because this is if I got the call, actually where you are answering and this question my professor found that wasn't quite the one that he asked, but okay, I had this question in mind myself. So if I got it right, I mean, you were kind of saying that these extra dimensions, because my naive understanding of string theory is that in the compactification case, use Calabi-Yau manifolds in order basically to wrap around space. And I think that, okay, people in string theory community take those extra dimensions to be physically real.
Yes.
So you are focusing here because of the gauge gravity duality on the deep brain side, basically approach to these extra dimensions. So in this schema, the duality, because on the right side with the ADS times S5, you have these closed strings that kind of pop into this sequence of slices, and that basically, well, I guess is space-time.
Yeah,
so,
space-time, they're all on top of each other. Yeah.
Yeah. So on the brain side, I mean, this embedded space, these extra dimensions. I mean, I don't know if it's ready to the low energy limit when you take basically, and these extra dimensions in the space is what basically kind of get neglected.
Yeah.
So I don't know if I'm...
Yeah. Let me try to draw this. Okay, try to remember this picture, but I'm going to draw it again and then go slowly. Sorry. So I shared. Can I share the screen here? Share the content. Yeah, share the content. Sorry, it takes a moment. Okay, I hope you can see my iPad. So let me try to draw some more things again. Okay, so maybe let me draw a table. Okay, so we have 10 dimensions. Okay, so let me make this a table. Okay. Sorry, it's not very pretty, but I hope you get the idea. Okay, so now so this is time, okay, and then I have 9 space dimensions. So now I want a D3 brain, which means I place an object in this, and this direction. Yeah. So if I place an object in this direction, so that's what I've been drawing here with my previous figure. This means that the directions 0, 1, unfortunately, I can't draw 10 dimensions. So I have this rather, so the directions 0, 1, 2, and 3 are long, and 4, 5, 6, 7, 8, 9, they go in this direction. Okay. And so now here, if I look at these open strings, okay, so they are attached here, and this thing can now fluctuate. And so in fact now I can write down some coordinate called x mu, where mu goes from 4 to 9, okay. And let me say the coordinates here I call, well, they will be x1, x0, x2, and x3. So these coordinates, they will be functions of x0, x1, x2, and x3, okay? Because so this capital X now tells me where my brain is located in space, okay? But then I can, the low energy, again, so physicists, they write Lagrangians, okay? So I can write a Lagrangian that depends on x mu and the derivatives of x mu's. And then, so these things are coordinates. Yeah, so these coordinates tell me where my surface is embedded in space. So if my hand is now the surface, it can be here, it can be there, and it can be there. And this is determined by this coordinate capital X. But now if I sit here, okay, so if I'm here in this world, then I can consider this capital X to be now a field in my field theory. So that's how the theory is made. So this means I have these extra symmetries in this direction here, but or I have the extra fields in these directions, and these extra fields are viewed as the fields in my Lagrangian. So the dimensions become the fields in this deep brain picture. Okay, so it's just okay. I know it's.
Okay, so if I'm getting right, I mean the vibrations of the deep brains is what basically account for these extra dimensions. Is basically what you are saying.
Yeah, exactly.
Okay.
Precisely. Yes, exactly. That's what I'm saying. Okay, so but this was now for the open strings. Okay, so now let's go to the closed strings. And so here the story is different. So I have a 10-dimensional supergravity theory. So, and supergravity means, so it's the low energy limit of superstring theory. And low energy limit again means, so if I look with a microscope, okay, I can't draw a microscope, so this is so this is meant to be a microscope. Okay, so I look here with into this microscope, and then if I look with the microscope, I see a string. Okay, but then if I look without the microscope and just look in my eye, then it looks like a small point, okay, because my resolution is bad, the energy is low, okay. So then, and this 10-dimensional supergravity again, so I have the coordinates x0, x1, 2, x9. And now I want this to be in a solution of 10-dimensional supergravity. So this means I want a supergravity metric, okay. Let's put these. So, sorry. Okay, so this is what people call a metric in 10 dimensions. So these capital X's are now the same X's as before, but in this other theory. So then I choose a particular ansatz for this metric that contains my, so some function, I don't want to get too complicated. So there's a function, so y squared is x4 squared plus x5 squared plus x6 squared plus x7 squared plus x8 squared plus x9 squared. So, and then here I have so, and this mu now goes from 0, 1, 2, 3. Okay, so this is the metric again here on the surface. Okay, but now so I think there's a half here, and if you look at my book, I just these numbers don't play any role. I just want to make consistency with my book. So, and then here again I have dx. Now let's use some other letter, alpha. Okay, and alpha now goes again from 4 to 9. Okay, so this is an ansatz for this particular metric, and if I put this into the equation of motion, which I get from my action, then again I get such a brain. But now in the closed string picture, which means, okay, so this is now my 10-dimensional space here, the sheet of paper. And then I get a solution where I have such a subspace, okay? And but the subspace is very heavy, and so it curves the space. Okay. But then now if I do the maths and take this ansatz and put it into the equation of motion for this metric, then I precisely get this anti-de Sitter space. And because I have 10 dimensions, there needs to be another space, which is a 5-dimensional sphere. Okay, so then I have this very heavy object and that curved space around it, and there's now these closed string excitations. This is the closed string picture. Okay, but now the ADS-CFT correspondence tells us, so this was the picture I was having here, so I'm drawing the same picture that I had before. So this is my open string picture, but the branes are the same, okay? So mathematically the same. So there's a duality between these two things. Because, okay, so what was the duality? I have a physical object, which in this case is now the D brane. And I have one theory that describes the D branes, and I have another theory. And it also describes the D branes. So there must be a relation between them, and this is the duality. Okay, so and now, so here I have my branes in the open string and the closed string picture. But these are the same objects here. Okay, so they must be the same. But then on top of this, now I take a particular limit. And this limit acts on each of the two scenarios. And in the one scenarios, it gives me this particular quantum field theory, the supersymmetric one, this gauge theory here. And in the other, it gives me classical gravity. But on this particular space, there's this hyperbolic space that I mentioned before. Okay. I know this is complicated, so but the idea is so we work at the level of string theory. We say we have these D branes, they are the same object, but they can be described by two different theories. So these two theories must be related by a duality. And then we take a particular limit. So this is what is in this Maldacena. So the reason why Maldacena is famous because he found this limit, really. Okay. So then in this limit, this gives me, so this is a gauge theory without gravity. And this is obviously a gravity theory, okay? But they must be dual, because if there's a duality here, there must also be a duality there, because I'm taking the same limit on the two sides. Now at this level here, it's very hard to calculate anything. But with this theory here, we can calculate very well. And so we can perform tests on this conjecture. Okay, so there's one other thing I wanted to say about this. Wait, maybe I should pause. So are there further questions about this?
Yeah, Johanna, maybe a quick question. Intuitively, what guarantees the fact that this low energy limit preserves the duality between open and closed strings?
Okay, very good question. Okay, so let me give you more details. Okay, okay, so so here I just wrote QFT and here I wrote classical gravity. Okay, so now let me be a little more precise which QFT. Okay, so the QFT that we have is this so-called n equals to 4 SUN. Okay, you have to be careful because there's two different n. So there's a curly n. The curly n is equal to 4, which is related to the supersymmetry. And the straight n is a different n, which is related to the gauge symmetry. Okay, so there's a curly n, a straight n, they're different. And this is the so-called super young Mills. Okay, and this theory, so again, so this is a gauge theory. And this has some fermions. And then it has 6 scalar fields. And then it's not a coincidence that it has 6 scalars, because the 6 scalars are precisely those of these 6 dimensions. So these 6 fields, x4 to x9. Okay, so they appear here in our Lagrangian. So there's a kinetic term for these scalars. Okay, so they enter this Lagrangian. Okay, so now the duality at the level of string theory is that this should be dual to so-called, okay, I just dropped some names. Okay, it doesn't matter if you haven't heard this before. So this is dual to the so-called type 2B superstring theory on alias 5 times S5. Okay. All right. So now let me explain the limits. So because I said this limit was so important. So, okay, here I should write a G. So there's a coupling constant here, which is the coupling constant of this gauge theory. And so now there's a twofold limit, actually. It goes in 2 steps. So the first step is that I define a quantity called lambda. And lambda is the so-called Turhoff coupling, after this famous Nobel Prize winner Tuft, who already found a long time ago that the perturbative expansion of the theory organizes in a beautiful way if you use this coupling instead of the original one. So this is our original gauge coupling. This is the straight n, which is the rank of this gauge group. So this one, okay. And this coupling is called the Tuft coupling. And then, so now in fact, so you see there's a left and a right side of this diagram. So here we are in the QFT side, and this is the gravity side, okay? And so now it turns out that, so if this is the Young-Mills, the field theory string coupling, let me just tell you that the string theory coupling constant is the Young-Mills coupling constant squared. Just accept this now. Okay, it's too long if I explain where this comes from. So, but this means now, obviously, so doing the maths, if I take this lambda to be fixed, but take a limit where this n goes to infinity, then this obviously just by a simple algebra, this looks like this. Okay. Okay. I define G string to be G Young-Mills squared, but G Young-Mills squared enters, so lambda is G Young-Mills squared times n. Okay. So now this by simple algebra implies that G Young-Mills squared is lambda divided by n. Okay. And so this means if I keep this fixed but send this to infinity, then obviously this thing goes to 0. Yeah, so then this means the limit in which I send, so that's why I said before, we must send n to infinity. Okay, let me rub this thing off here at the bottom. So the limit where n goes to infinity means that, well, this is a particular limit of this field theory where I take this n to be very large. And so this is a thing I mentioned before. I mean, QCD, this n is equal to 3, but it's a very inherent fact of this duality that n goes to infinity. We cannot remove this simply. And n infinity then here means that the string coupling goes to 0, which then means that I have classical string theory. Okay, so if the coupling constant goes to 0, I have no more loops in my perturbative expansion, and it just becomes a classical theory. So that was limit number 1. But now there's also a limit number 2. The limit number 2 is that I send this lambda also to infinity. So far I put just n to infinity. Now I put also lambda to infinity. And then the theory becomes strongly coupled. So that's what I mentioned before. Okay, so this was this picture I showed. This means all the particles, they are kind of linked by all these little springs. Okay, so you cannot do perturbation theory anymore, and you have to solve the whole system at once, and this is very hard to calculate anything with this. Okay, but on the other hand, it also, another fundamental relation is now that this lambda is actually, let me get the units correctly. No, sorry, there's no square there. One more time. Lambda is L squared over the length of the string squared. So this L we saw before, this was this ADS radius. So it's the geometrical quantity of this antithesis of this hyperbolic space. Okay, so that's inherently in your construction. And LS is the length of the string. So this means if I make this very big, and this is constant, so then means lambda going infinity implies that the length of the string goes to 0. And if the length of the string goes to 0, it means I have point-like particles. Okay, and so let me just take another color. So I have two limits. I put n to infinity and lambda to infinity. And so the question was, why does the limit preserve the duality? Okay, that's what I'm trying to answer. Okay, so because n goes to infinity, lambda goes to infinity, it means the theory becomes strongly coupled with, on top of that, n to infinity, which is a kind of semi-classical limit, which is the so-called Tuft limit, according to Gerard Tuft. Yeah. But so I know exactly what these limits do to the string theory. The first limit is they take me to classical string theory, and they take me to point-like particles. So in total here, I end up with classical gravity of point-like particles. Okay, long story short, I know exactly what these limits do. Okay, so here, so I have n to infinity, lambda to infinity, which means G string goes to 0, and the length and the coupling of the string both go to 0, which then means that I end up with the classical theory of point-like particles. So yes, I know for sure that the limit, I mean, this is exactly what is in this Maldacena 1997 paper. Okay, so that's why he's so famous. That if I take n to infinity and lambda to infinity, this I know from the entire construction that it corresponds to the fact that the string coupling and the string lengths go to 0. Okay, so these things are the same. And so this means from this construction, so starting, so now I think I can go back to, okay, maybe let me pause one more time. Okay, so now it was getting very messy. So we start with n equals to 4 SUN super Young-Mills theory, which is a quantum field theory. And so the conjecture duality, so this is open string and closed string. So this is type 2B string theory on ADS 5 times S5. Okay, and the limit now is that I take n to infinity So this n is this n, and I take lambda to infinity. This implies that the string coupling goes to 0, and this implies that the length of the string goes to 0. And then here I end up with the same theory, but now it's strongly coupled and semi-classical. So this n to infinity is a kind of subtle point approximation, if this means anything to you. And here I get point like classical in gravity. Okay, so and then because I know, or I mean, in string theory, I can conjecture there's a duality here. And since I know what these limits do, and this limit is very, very, very well under control, I know exactly what this limit does on the two sides, then there must also be a duality here. Okay, and this is the duality that we talk about. So here there's no gravity, and there's gravity. So, you know, that's what I was saying before. If somebody tells you, I mean, here I have a theory without gravity, and here I have a theory with gravity, and they are just the same, I mean, there's no reason why you should believe this, but the reason comes from this entire construction that is now on this sheet, on this picture, because it's really a duality of string. And then there's a limit which is extremely well under control. I know exactly what this limit does. And then I end up with the duality at this level here. Okay.
Sorry, can I ask a question?
Sure, sure.
Sorry if now I can.
Go
All
ahead.
right. No, sort of clarification, brief clarification. So if I understood well, when you talk about quantum field theory in this schema, you are talking about a particular quantum field theory that is supersymmetric, and so yes. Okay. And when you talk about gravity, you are talking about a solution of that is the anti-de Sitter spacetime.
Yeah, exactly.
And in higher dimension. So I have two points. The first point is also related to the fact that we discussed earlier on the physical meaning of the dimensions, etc. So the point is, what is the physical point on saying, yeah, there is a duality between a quantum field theory that is not natural and a theory of gravity that is not natural.
Yeah.
And the second point is, I mean, where is in this schema general relativity? Because you are deriving a particular solution of Eisenfield equation, but I mean, I think that also because you're assuming, so you have a topological assumption, and I'm not sure that assuming this topology will save, for example, background independence. For example, if you do a Klein-Gordon theory in the Sitter space-time, you assume a particular topology, and globally you have a background structure globally, so you lose background independence, so you don't have a full general relativity. So when you write GR, I mean, you have a particular solution of Eisenfield equation that is general covariant, yes, but general covariance is not what distinguishes general relativity from the other physical theories. I mean, also Newtonian theory can be written in a general covariant way. So these are the 2 points I
okay, good. So the first thing, I mean, why? Okay, so I know that everything which is on this page is purely academical. I mean, none of these things exist in nature. But here in this picture, everything is super nice under control. And I mean, one thing okay, so because on top we know that the symmetry, okay, sorry. Symmetries, so this is symmetries agree. And we also know the number of degrees of freedom, they also agree. agrees. Okay, so just for in mathematical terms, so here the symmetry, the global symmetry. So I'm not talking. So this is so far I talked about the gauge symmetry. So by the way, somebody else asked before, how do I see the gauge symmetry on the gravity side? Well, the only way you see it is precisely in this relation here. So the rank of the gauge group appears in this relation to the string coupling, but I mean, there's no gauge symmetry here present on this side. Okay, so that was just a side remark to this earlier question. Okay, so first of all, we know that the global, so I should say the global symmetries agree. And this symmetry is, okay, so there is an SU4 symmetry. This is a group theory, okay, so which this 4 is the same as this 4. And then the conformal symmetry has a group called SO4,2. Okay, so it's just names. But then this S5 also has an SU4 symmetry. I mean, for those of you who know group theory, because the symmetry is isomorphic to SO6, okay, and that's the symmetry of a 5-dimensional sphere. But this anti-de Sitter space has also SO4,2. Okay, ignore all this group theory. The only thing I want to say, this global symmetry is exactly the same as that global symmetry. So as I was saying before, I know that the symmetries are the same on the two sides. And I know the number of these degrees of freedom agrees, okay? So, and that's already two extremely good reasons that these two theories should be the same. Although this theory will have a totally different Lagrangian of that one. Okay, so yes, it's an academical example, but it's one which is under extremely good control. So you can view this as a kind of toy model. And in my other lectures, I want to explain to you that that we can also do this for theories which are more realistic, but then of course there's less symmetry and things become more complicated. So in physics, it's always good to start with the simple things first, even if they're not realistic. Okay, so in this example, I have extremely good control because there's so much symmetry. And so I know what I'm doing. Okay, so that's always a good feeling. And so if I understand this example well, then let's move on later to see. So for instance, this shear viscosity thing, which appears in nature, you know, this is the next step. Okay. So in physics, it's always good to go in small steps. Stick with the things that you understand well, and then you go to the next step and so on. And I know this is totally academical and not real, but it's mathematically under extremely good control. So then once we understand in this kind of toy model how things work, then we can think about more complicated theories where we talk about the real world. Okay, so yeah, it's academical, but it's well understood. Now the second question about the general covariance. Okay, so yeah, it's true that it's string theory on a particular background, but nevertheless, in the end, I can write down the action of this theory. Okay, so which is which looks like this. So and now I'm in 5 dimensions, and so it's a gravity action. So I have a Ricci scalar and then a cosmological constant. Okay, so this is my theory, and it's totally covariant and so on. And I can show that this action for this ADS5 part actually arises from this string theory. Okay, so just believe me for now, otherwise it gets complicated. But so we have an Einstein-Hilbert action here. And this Einstein-Hilbert action has a negative cosmological constant. Okay, and then I write down the Euler-Lagrange equation for this action, and then I find that ADS5 is the solution of this. And then I can expand around the solution, but nevertheless, I have a totally covariant action, which is this action. It's just an action with a negative cosmological constant here. So we do have general coordinate invariance. I mean, because we start with a quantum gravity theory, so we have a general covariance all the way along here. It's just that ADS is a particular solution of this action. Okay. But this is a totally okay action in general relativity. Yeah. I hope that answers your questions.
Yeah. Okay.
Thanks. All right, anything else? So very good questions. I hope things become more clear. Any other questions? Good. Okay. So I tried to explain this figure. Okay, so just to summarize, there's some object called D3 brane that you can consider in the open and closed string pictures that are related by a duality, and then there's a particular limit due to Maldassina, which takes one of them to a quantum field theory and the other one to a gravity theory with a negative cosmological constant. And since they are related by a duality here, then these two theories should also be related by the same duality, because this limit is under extremely good control. Okay. Next, so why I explain, the reason I explained all these things about string theory is to say that there's a reason why these theories are related to each other, which comes from the string theory construction. But okay, so the next step now is that I showed you a relation between theories at the level of their Lagrangians. Okay, so I have two theories given by Lagrangians, and I claim that these theories are the same theory, which is called a duality. But now, then I also told you that it's hard to prove this theory. I will explain in more. I mean, maybe this already appeared a little bit in this discussion which we had before, because if you really want to prove the correspondence, you have to prove it at the level of string theory, not at the level. So you have to prove it at this level and not at that level. But it's a bit hard to formulate precisely the dynamics of this theory in a non-perturbative way. I mean, that's one reason why this is not so easy to do. But if we can't prove the theory, at least we should kind of have some examples where it's shown to work. So if I tell you the Lagrangian of the theory is dual to the Lagrangian of that theory, I should be able to do some calculation for this theory and do the same calculation for that theory, and the results should agree. And that's in fact possible. And the way this works, that's what I want to explain next, is based on the so-called dictionary. Okay, so now this is now a cartoon of my 5-dimensional anti-de Sitter space with this extra dimension, and this space has a boundary on which, and actually the boundary of anti-de Sitter space is again Minkowski space-time. Okay. So I have a d-dimensional quantum field theory, the one we discussed before, defined here at this boundary. And I have a gravity theory in this hyperbolic space. So now I claim that this Lagrangian is the same as that Lagrangian. So how do I test this conjecture? Well, and in fact, I can make this map now extremely precise using the huge amount of symmetry that I have in this theory. And I can look at group theory representations in one theory and the other, so they have to be the same based on mathematics. Okay. And so I can define some particular operators in this quantum field theory with particular symmetry properties. And then the claim is that in this theory, the classical gravity fields here with exactly the same properties, they should be in a one-to-one correspondence to these field theory operators. Okay, so that's referred to as a dictionary. So because I have a one entry on one side and one entry on the other side, and there's a bijective map between these two. And okay, so how do I establish this map? By choosing operators whose symmetry properties coincide. And now there's various tests of the correspondence. For instance, I can calculate correlation functions. So now I can calculate a correlation function just using standard quantum field theory techniques for calculating correlation functions. And so I calculate this correlation function here. And then I can calculate the same correlation function by a gravity calculation, which is classical. So here this wiggly line means that there's a Feynman diagram quantum computation. But then I do the same calculation on this side of the correspondence by a classical propagation, but in one dimension higher and in this hyperbolic curved space. And then, so the two calculations look completely different, but nevertheless, I get the same result on the two sides of the correspondence. So here, this quantum calculation using Feynman diagrams gives the same result as the gravity calculation using the propagator in this curved space. So I do these calculations actually quite complicated. Okay, so I show them, I teach a course on ADS-CFT to my undergraduates here in Würzburg, which takes the entire term. And I do these calculations, but certainly just to show these calculations takes 2 lectures or so. So it's not a super easy calculation. And so it's impressive that 2 very different computations actually that are both quite involved give exactly the same result for the correlation functions. But then on the other hand, given the entire construction and the amount of symmetry that is there, I mean, it just can't be anything else, really. I mean, this is also an argument in physics that is used very often. I mean, the result just can't be anything else. Okay. That sounds a little ad hoc if you want to use logic, but I mean, this is an argument which is used quite often. And I mean, it's impressive that the results of these lengthy calculations agree, but on the other hand, it just got to be true. Okay, just given all the work that we put in, it just has to work, and it does. Okay, which is reassuring, I would say. Okay, so if I say there's a duality between 2 theories, it doesn't just mean that in the entire Lagrangians are somehow related, but also individual fields and operators in the 2 theories can be mapped to each other. So that's the point of the slide. Okay, so this duality is really very precise. I can map individual objects in my 2 theories, and I can do calculations with them, and the results of the calculations agree, although the calculations are themselves quite different. Okay, so that's what I wanted to emphasize here. Okay, so this is one of the very few equations I want to show to you, but I think it's important. So this is precisely the starting point for this computation that I showed on this slide. And well, I mean, here there's an equation, but essentially the text below is exactly the same statement as this equation. Okay, so let me read the text. So the statement, so this is the ADS-CFT correspondence in one equation, which states that the generating functional for correlation functions of particular composite operators in the quantum field theory coincides with the classical tree diagram generating functional in supergravity. Okay, so there's an equation, there's an equal sign. Well, essentially, this is the generating functional of the conformal field theory, and this is the generating functional of the gravity theory. And well, if you know, I mean, the reason I'm showing this because it gives yet another flavor to this word duality. Okay, because here you have an integral over the product of 2 functions, and mathematically, this is also called that these 2 fields are dual to each other. Okay. And so this is an operator in the quantum field theory, in this conformal field theory. And this operator comes with a so-called source. Okay, so that's the definition of this generating function. Okay, so the operator comes with a particular source, which means that if I take functional derivatives with respect to the source, I get correlation functions of this operator. And so this is a mathematical definition of the word duality here. And so the only condition that I have to place is that on the gravity side, I have also a generating functional, but there the sources, so this function here, which is on, so this side of the equation is field theory, this side of the equation is gravity. So the fact that I equate them is a relation between quantities in the field theory and quantities on the gravity side of the correspondence. So the only thing that I have to impose on this side is that I have to impose that the boundary values of the gravity fields that occur in this gravity action coincide with the sources for these operators here. So this phi naught function is the same as that. So what's phi naught? So let me go back one slide. So you see here, you can imagine where these blobs are. This is where a so-called operator insertion of this operator O is. And this I get via functional derivatives with respect to the source. And so normally this force is just some classical function that doesn't do anything. But the new thing now is that I make it a dynamical object. So it becomes the boundary value of this dynamical field that propagates in this extra dimension. So here I have a classical gravity field that propagates here, and I identify its boundary values with the source of these operators in the field theory. Okay, so that's a technical term just to saying that I demand that the boundary values of this field, so phi is this field that propagates along this red line here, is identified with the source for this operator here. Okay. And so if you don't understand the maths and definitions, this is really one equation where the left-hand side is quantum field theory and the right-hand side is gravity. And so I just impose a boundary conditions on these dynamical fields in the gravity theory that comes from this field theory side here. Okay, I don't know if this was too much equation, but I just wanted to say, I mean, you can really write the ADS-CFT correspondence in one equation, and this is the equation. Okay, so are there any questions about this? Okay, the statement is, if I have this one-to-one map between operators and fields, I can really do computations and compare the results. And so it's really very hands-on. So I use techniques that physicists learn while they are undergraduates. Okay, so which you can learn in undergraduate physics course. Okay, okay. So and now this brings me back to this diagram which I've drawn before. So on one side we have this quantum SUN gauge theory, which according to this open closed string duality is conjectured to be dual to a quantum theory of gravity, which is a string theory. And then there was this double limit, which I explained with n going to infinity, lambda going to infinity. So n to infinity is really amounts to a so-called saddle point approximation, if this means anything to you. And then, so here we get the same gauge theory, but in the limit where this n is taken to be large. And this very complicated, difficult to handle string theory becomes then just essentially classical GR. And then since we conjecture this duality and this limit is and then extremely good control, then we also have a duality at this level here. Okay, but this diagram also shows why it's so hard to mathematically prove the correspondence or the duality. Because to actually really prove it, you have to undo this limit and prove it at this level here. Okay, so this was this low energy limit that I explained. And so undoing this limit takes you to this string theory in this curved space background of ADS 5 times is 5. And okay, so while quantum gravity theories around flat space, there you can use perturbation theory. This theory is not under such good control. I mean, you can explain what a brane is in this theory, but it's very hard to actually do explicit computations here. So I would even go as far as say, okay, this is not well defined in a mathematical term. I mean, you can postulate that this theory exists, but it's not really clear what this actually is. So if it's not really clear what it actually is, then of course you can't calculate anything. And if you can't calculate anything, then also you can't prove. I mean, you know, if you tell a mathematician prove that this is equal to that, but I can't define this, then mathematicians will tell you, well, okay, good luck. I mean, this is not going to work. Okay, I mean, if you want to prove something, you have to have ingredients that are well defined. But okay, this is well defined for physicists, but not for mathematicians. And and that's why it's impossible at present to actually prove this duality. Okay. So that's, I mean, of course, you should remember this diagram, but also the second information here is that it also gives some hint why it is very complicated to actually give a mathematical proof for the duality. Okay, any questions about this?
Yeah, we have one here.
So if you maybe say, is this one? Okay. If you could maybe say a bit more as to maybe why you say that the physicists take the string theory side, right, to be reasonably well defined, when mathematicians say that, well, no, we do not really have a definition that is precise enough, and like what is missing that the mathematicians want in order to have the quantum size of this duality to be well defined, and then we can try to actually prove this in a way that is satisfactory. Yeah, okay. I mean, so the problem is, I mean, you can say, okay, I want to quantize string theory. So, you know, I mean, there's a twofold. There are lots of technical problems, I would say, okay. So one problem is that normally if you quantize a theory, what is well defined is perturbation theory, and then you do a loop expansion about some background solution. And in string theory, that's well defined if you perform this loop expansion about flat space. But here we don't want a loop expansion about flat space, we want a loop expansion about this ADS 5 times is 5. And already this, nobody knows how to do it, okay? And then the other problem is that even we are beyond the regime of weakly coupled perturbation theories, and really it's a strongly coupled quantum theory, and then really we can't do perturbation theory. Okay, so already the perturbation theory is not well defined, but then also you have to go beyond perturbation theory. So this means, I mean, you can write down the classical action, and you can say, this closed string picture. I mean, here, I mean, this is really this geometry is a classical solution, which is kind of the zeroth order, if you want, in perturbation theory. But since anywhere we take the limit where the string coupling goes to 0, that's exactly the limit we need to go here. But if you want to prove the whole thing, you have to go back to the quantum picture where the string coupling is not 0. And so then A, it's not possible to do the perturbation theory expansion about the flat space background, and B, even if you knew how to do that, that's not really what you need. You need a non-perturbative treatment, and I mean that's just non-perturbative quantum gravity. I mean nobody knows how to do this. I mean, and so what we have is we can write down the classical background about which we want to expand, and say, and so we want the quantum theory of this. Yeah. But that's not enough to actually prove the duality, because then you would need the solution to this quantum problem to actually show that. I mean, you know, there is ways. I mean, there in much more simple cases like this massive Thirring Sine-Gordon duality. You can actually prove the duality by saying this object is precisely mapped to that object. Okay. And you can really do a transformation where you transform the one Lagrangian into the other. But this is not possible because we cannot write the quantum Lagrangian. Okay, so the physicists say this is our classical theory and we want the quantized version of that. Okay, but this doesn't mean that you can write down the quantized theory. So and then you can't prove anything. So, okay, so the answer to your question is nobody knows the techniques to quantize this particular theory. So, and
then you can say we want a quantized theory, but you don't know how to get it, and that's why you can't really prove anything. I mean, I'm not saying that it's impossible for all ages to prove this. I mean, maybe someday some clever person come. I mean, this is what I tell my undergraduates, you know, if you want to be famous, you have to make some big improvements in string theory and write down this, at least the perturbative expansion, maybe also a non-perturbative version of quantizing string theory on ADS 5 times 5, and then you can possibly prove this and you will be famous. I mean, I'm not saying that this is impossible to do. It's just in the last 25 years, nobody managed to do it. Okay. That's the problem. So it's technically involved, and so far nobody managed to do it, but this doesn't mean it's impossible. Maybe some clever person one day will find a way of doing it. I think that's the answer to the question. Okay, good. Any other question about this? Good. Okay, then, all right. I think tomorrow morning I should, we start at 11, isn't it? I will repeat this diagram because, I mean, it's super crucial to understand this, and maybe I should repeat one more time. Okay, so now to the question that many people ask, okay. I mean, there's some theoretical physicists who actually never care if anything is real or not. I mean, this question was already asked a couple of times, but, you know, I would certainly care that, you know, my theories describe something in nature, okay, because I'm a physicist. But I mean, there's certainly a number of theoretical physicists who don't care that their theories are not realized in nature. So, but of course, okay, we are physicists, so it should be realized in nature. And okay, so far I told you about this very academical example where we have all the symmetries under control. But it's very academical because this ADS-CFT correspondence, as I showed to you with this ADS space and the conformal field theory, that's certainly not realized in nature because the nature is just not so symmetric. Okay, so it's a toy model because we assume a lot of symmetries to be present. And that makes life more easy, but on the other hand, it doesn't. I mean, this is always the trade-off. I mean, you make things so symmetric. If you make things very symmetric, you can solve everything, but then they don't describe anything anymore in the real world. So, but nevertheless, it's a good idea to start with something that you have under good control, even if it's not realized in nature, and then try to work your way from there. Okay. So as I told you this afternoon, string theory provides us with the best understood example of gauge-gravity duality. So best understood in a theoretical sense, okay, where you know we can really, as good as possible, map these theories to each other. So it provides us with the best understood example of gauge-gravity duality, and the name of this duality is ADS-CFT correspondence. And so what you should remember is that ADS-CFT is a particularly symmetric example of gauge-gravity duality. Good. So now I used a lot of string theory to motivate the ADS-CFT correspondence. And now, so if you asked me 10 years ago, I would have said, ADS-CFT only makes sense within string theory, okay, because there's the story of the brains and so on. So if you don't have those brains, you know, then it's very hard to motivate where this comes from. Now, but then you might ask the question, can this duality be established independently of string theory? So that's certainly a very valid question. And I don't think there's a definite answer to this yet. But there were a lot of developments, and so I'm mentioning this because I want to make a connection to the other talks in the school, okay, where there's very, very interesting talks devoted to this connection between gravity and information, okay. And so this is a very recent development, like this ER as EPR and so on. So this is a very recent development, which I think is super interesting. So I said that string theory provides us the best understood example of gauge gravity duality, which is the ADS-CFT correspondence, which is this very symmetric example. So now the last thing I want to discuss today is the question of gauge gravity duality can be established independently of string theory. And I said that I personally certainly changed my mind about this, but on the other hand, this is not an this is an unanswered question. I mean, you know, there's a lot of debate about this. And, so given what I told you this afternoon, there was a lot of string theory in my discussion. So certainly, I mean, without string theory, people would never have found the ADS-CFT correspondence. I mean, that's for sure. Now the question is, can you realize such dualities without resorting to string theory? And so I mentioned this recent development that also the other lectures in this school will address, which is the relation between information and geometry and like ER is EPR, for instance. And so this is a recent development which gives some hope that actually these dualities are valid more generally than in string theory. And I'd like to discuss a few aspects of this. But certainly, I think we should remember, without string theory, people would never have found this duality. And certainly, if we want a proof, it should be as proof within string theory, probably. Okay, so let me make some remarks about this relation between gauge gravity duality and quantum information. And so there was already a glimpse of this when I mentioned the black hole entropy. And there was this famous Bekenstein-Hawking formula that told us that the entropy of a black hole and its information content is related to its area. Okay, so that's a classical example of geometric object related to an information object. And so the use of geometry is widespread in information theory. I will show you an example. And so the idea is to make use of this to gain further understanding of gauge gravity duality. Okay, so one concept that's particularly useful in this context. So information theory, or there's also even a field of mathematics called information geometry. And so what people do there is they look at probability distributions that contain some information content. And then they do geometry with this. So they define, you know, lots of differential geometry quantities such as metrics and geodesics and distances and so on. And one particularly useful concept here is the so-called Fischer Metric. So, and this was known in the 70s, so a long time before the ADS-CFT correspondence. And there's a surprising connection here, which I wasn't aware of for a long time, but it's actually very important. So the Fischer metric, so Fischer is a mathematician. So this is a metric on the space of probability distributions. Okay, so you can construct a mathematical space which is built out of probability distributions. And then if you have a space, you can also have a metric. Well, in this particular case, yes, certainly, yes. Okay, sorry about the equations, but they're not so complicated. Let me try to talk you through this, okay? So I want to explain what the Fischer metric is. So it's a concept in this information geometry. And the upshot will be that if you write this, so the simplest probability distribution that you can have is a Gaussian probability distribution. And so if you calculate this metric for a Gaussian probability distribution, then you obtain an anti-de Sitter metric, okay? So which I find is quite striking. Okay, sorry about the equations. Let me very quickly explain what this is. So assume you have a probability distribution called P, and so which depends on a stochastic variable called X. And then you have a vector theta, which is a set of n external parameters that you have in your probability distribution. Okay, and then mathematicians like to define a quantity called a spectrum. And the spectrum is just defined as minus the logarithm of this probability distribution. Okay, so now the Fischer metric is the metric on the space of probability distribution. And so this is the mathematical equation that realizes this concept. So we have an integral over the stochastic variable. So it depends on the set of parameters. We integrate over the stochastic variable. So this is the probability distribution itself. And then we take two derivatives with respect to the elements of this set of external parameters of the spectrum, which is minus the log of the probability distribution. So what you get here is really the expectation value of the product of two derivatives of this function gamma with two indices mu and nu, because you go through twice through this vector of parameters. And now the super striking thing is the following. If you take a Gaussian distribution, which is the simplest possible probability distribution you can have, and so this is one thing I didn't mention in all this discussion this afternoon. If you do this so-called saddle point approximation, which comes from this large n limit that I was mentioning before, then even if you have a strongly coupled theory, your probability distribution will be a Gaussian distribution. So if you take this n=4 SUN super Young-Mills theory that appears in the ADS-CFT correspondence, and you take this limit where n goes to infinity, then you know that your probability distribution will be a Gaussian probability distribution. Okay, and here you see a Gaussian probability distribution. So there's an exponential of the distance to some mean, and the sigma is the so-called variance. Okay, so the x bar tell you where the peak of your distribution is, and the sigma tells you how broad your distribution is. Okay, so if the sigma is very small, you get a very peak distribution, and if the sigma is very big, you get something very flat like this. Okay. And now the very surprising thing is, if you take this probability distribution that presumably you get from your quantum field theory, and you plug it into this definition for the Fischer metric, and you calculate this expression, then you get a metric of an anti-de Sitter space, okay, which I find extremely striking. And so the Minkowski boundary coordinates are given by the maximum position of the probability distribution. And this extra radial direction is given by the variance of the probability distributions. Okay, so going back to our picture, this means, so if this is the boundary of the anti-de Sitter space and this is the interior, so this extra dimension is now given by the variance of the probability distribution. This means if I'm here near the boundary, equivalently in the field theory, I have a very peaked distribution, okay, so where the probabilities are all very close around some mean. But if I go far inside, then my distribution, so the coding becomes very big, and I get this very flat distribution, okay, where almost everything has the same likelihood of arising. And I think this is super compelling because it gives a very nice relation between a metric for some probability distributions in the context of information theory and a geometrical objects that precisely arises in our discussion of the ADS-CFT correspondence, which was this metric in anti-de Sitter space. That's super nice, but of course, yeah, question?
Yeah, perhaps you're gonna say next, I don't know, but I find it a bit puzzling. I mean, because what's the interpretation of this Fischer metric?
Yeah, that's exactly that's what exactly I wanted to say.
Okay, cool.
It's super nice, but we have no idea what it means. Okay, and so okay, that's exactly what I wanted to say. So in this entire discussion of string theory, which took us the entire afternoon, and I tell you these dualities and limits and there, at least I have a very well-defined construction, and I know exactly which Lagrangian I have to write down on the two sides of the correspondence. I have this Lagrangian of the NX-4 super Mills, and I know the Lagrangian of the gravity theory and so on. Here I have nothing. Yeah, I have just this very general fact that by coincidence, okay, if I start with a Gaussian probability distribution, I get an anti-de Sitter metric, but there's no dynamics. I have no action that tells me that this must be the case. Okay, it's just an observation. Okay, and that's precisely what exactly. Thanks for asking the question, because that's exactly what I wanted to say. In the string theory picture that I talked about before, everything was complicated, but nevertheless, I knew what I was doing. Okay, so there were some rules. I was following the rules of string theory, and we got this duality. Here, this is very nice because we get a connection between two different objects, from information theory and gravity, which somehow must be inherent also in this correspondence, but there are no rules. So I cannot tell you anything about dynamics. It's just a kinematic observation. I mean, by coincidence, these things agree, but I have no idea why. Okay, so it's this is precisely the point. I mean, it is ad hoc. I mean, but nevertheless, while being ad hoc, it's quite interesting that this happens. But so this really poses a question. Okay, so so this is my question. So why am I discussing this? Because I said, can gauge gravity duality be established independently of string theory? That was the question I wanted to address. And so this argument shows a striking relation, but without string theory, I'm very much up in the air. I mean, it's not quite clear what I have to do next. Okay, so this is exactly the message I wanted to convey here. But I mean, of course, this is a matter of research. I mean, maybe we will find out. I mean, so this, maybe it's possible to find out a relation between this information theoretic concept and ADS-CFT without resorting to string theory. And many people are thinking about similar questions. Okay, but it's much harder than just to follow the rules of string theory, where at least you have a framework where you know what you are doing, and there's some rules that you can stick to. Okay, so that's why I was showing this example. Okay, question. Yeah, so the open question, and it's very hard to tackle because really there's no prescription how this should be done, is to understand the dynamics that governs this particular metric. Okay, so the message I wanted to convey is that in ADS-CFT, the gravity action and dynamics are obtained from the subtle point approximation of the string theory. Okay, so these are well-established rules where you know what you're doing. And so then the hope is that information theory may help to establish the gravity dynamics more generally without resorting to string theory, but of course, this will be much, much harder to do. Okay, so I should probably wrap up and just say the next topic here in this context is the famous entanglement entropy. I'm not sure if anybody mentioned this already yesterday. So then maybe I should be brief, but so this would now fit in this context here. So this is a conjecture in the context of ADS-CFT. Where you map the entanglement entropy defined on the boundary field theory to the gravity theory in the interior, and it has lots of nice features, but you can, in some sense, do this little outside the context of string theory, but then of course it's very hard to say which Lagrangian you are actually talking about, and what I was deriving this afternoon gives you this enormous amount of control over which Lagrangians exactly are you talking about. Okay, if you heard this yesterday, maybe I shouldn't spend too much time now, but I mean, this is exactly where this would fit now in the context here. But okay, so let me give you a plan for what I want to do in the next lectures. So I want to go to these applications to the strongly coupled system. So remember what I told you at the very beginning of the lecture today. There's this relation between this quest for understanding quantum gravity on one hand side, but on the other hand, really using ADS-CFT to describe these strongly coupled systems, which are very hard to treat otherwise. And I want to show you a number of examples where this has been done successfully. But then again, I mean, in some sense, you know that you are applying a theory which doesn't really fit your problem. But then if you have some very good arguments, like the one with the universality, you can still claim that the problem you're looking at doesn't depend exactly on the individual degrees of freedom you're considering. And nevertheless, although you're not exactly considering the theory that you want, the strong coupling approach can still provide you with useful information. And that's what I want to explain tomorrow and also Thursday. Okay, so I should probably leave it here for today and just ask if there are more questions now. So any further questions?
Can I ask a bit? Just I'm curious about, so there are these kind of famous mathematical conjectures like the Yang-Mills gap. So is it possible that can ADS-CFT is it stated precisely enough that it becomes a proper mathematical conjecture, or is it still based on a lot of sort of physical ideas that you can't formulate?
Okay. I would say, I mean, you could ask a claim millennium question, prove the ADS-CFT correspondence, but I think it would be probably even harder than proving the Yang-Mills gap, because at least in the Yang-Mills gap, the theory is well defined. I mean, okay, what's of course not well defined and makes the problem is the strong coupling. But here, in this case, I think more work needs to be done on the string theories. I mean, it becomes really a problem in string theory in defining a kind of background independent way of quantizing string theory. So if you were able to do that, and I think the proof probably will be a lot easier than it is today. So yeah, I mean, you might well put this on the millennium list, but
so it is precisely enough stated to be able to put on a millennium list. Okay.
Yeah. Okay. So if it will boil down to the question of finding a non-background independent way of quantizing string theory, which is I think that's the statement. If you can do that, then probably will be quite straightforward. I mean, just speculating to prove the ADS. I mean, okay, but you're right. I mean, it's certainly at the level of being precise that you can put it on this list if you wanted to. That's for sure, yeah. But then it would be, of course, the ADS-CFT correspondence within string theory that I was talking about this afternoon. If you now say, okay, let's make these nice connection dualities between theories in a broader context, then of course it becomes a lot more speculative. Okay, you might also ask if ADS-CFT can help you to solve this Yang-Mills gap problem. But then I think you're just trading one hard problem for another hard problem. And yeah, I mean, of course, ADS-CFT provides more information about strongly. I mean, this is a little bit what I'm going to talk about tomorrow. And you can actually calculate things in strongly correlated gauge theories, and I can calculate meson spectra and so on. But then, of course, there again, this large n limit comes in, which makes the theory semi-classical and so on. So I mean, solving QCD is still a long way away, because then QCD has n equals to 3. And going from n to infinity to n equals to 3 is just going from this simple to this complicated version of ADS-CFT. Okay, so I would say these problems are even related to each other. Yeah.